Hereby, I open the academic ceremony in which Amir Khaki will defend his academic thesis titled Environmental Stress, Cracking Resistance in Recycled High-Density Polyethylene. Dear candidate, may I kindly invite you to present a summary of your study and the conclusions of your thesis.
Dear Prorector, thank you for the introduction. Dear highly esteemed members of committee, supervisors, colleagues, friends, my wife, welcome to my PhD defense. A warm welcome also to the online audience, as well as my friends and family in Iran who currently do not have access to internet, but hopefully will watch this recording someday. In the next 15 minutes, I will present the main findings of my research on environmental stress cracking resistance in recycled high-density polyethylene, or HDPE. In simple terms, my research focuses on a key limitation of recycled HDPE, its low ESCR. Let me first introduce the motivation behind this work. Today, there is a growing effort to use more recycled plastics in new products as a part of transition toward a circular economy. In Europe, the Packaging and Packaging Waste Regulations, or PPWR, requires that plastic packaging must contain at least 35% recycled content by 2030. For rigid HDPE packaging, such as detergent bottles, however, one material property is particularly critical, and that is environmental stress cracking resistance, or ESCR. When exposed to surfactants, such as detergents, HDPE becomes more susceptible to cracking, even under low levels of mechanical stress in daily use or storage. This means that this material must have a sufficient level of ESCR to maintain packaging integrity. So the challenge is that post-consumer recycled HDPE often shows low ESCR than virgin HDPE in detergent bottles. As a result, the low resistance of recycled HDPE to stress cracking limits its use in producing new detergent bottles. To understand environmental stress cracking, it helps to first look at the structure of HDPE itself. HDPE is a semi-crystalline polymer. It contains crystalline units called lamellae. And between those lamellae, we have amorphous chains. Some of these amorphous chains that can connect at least two lamellae to each other are called tie chains. When a high stress is applied, the lamellae break and material can stretch significantly before failure. That is called ductile failure. Under lowest stress, however, the situation is a bit different. The stress is not high enough to break those lamellae, and instead connections between them, those tie chains, gradually disentangle if we give it enough time. As a result, the material can develop cracks without large deformation, which is known as brittle failure. Environmental stress cracking occurs exactly under the same conditions. Relatively low mechanical stress applied over a long period of time, combined with exposure to chemicals such as surfactants in detergents. This gradually leads to cavitation, fibrillation, and eventually brittle fracture. The role of tie chains in this failure mechanism is therefore critical. In simpler terms, if you have more tie chains in your polymer, it will have higher ESCR. As I mentioned, the main challenge here is the low ESCR of recyclates of HDPE, and it limits its use and production of new bottles. This was also the main reason our industrial partner initiated this project with us. The first question we asked was why recycled ESCR has why recycled HDPE has lower ESCR than virgin bottle grade HDPE. We tried to address this question in chapter 2 by a root cause analysis through design of experiments. And then the second question was, is there a kind of additive that we add to this polymer and improve this ESCR and prevent ESCR loss in recyclates? And for that, we did, in chapter 3, a systematic screening of industrial additives. Finally, we found an additive that could improve ESCR, but in the literature, there was no explanation for that. So we tried to dive deeper and address that question in chapters 4 and 5, where we try to investigate the mechanism behind this improvement in ESCR. Let's first start with the first question. Why do we have low ESCR in recyclates of HDPE? In the recycling world, the common explanation usually is contaminations. And in this case, of course, we have PP contamination, polypropylene, coming from the bottle caps. And we usually end up with recyclates that have some levels of PP contamination. However, if you can look here, you see that a polymer with a higher concentration of PP contamination shows higher ESCR. It seems contradictory, and it means that PP contamination alone cannot explain this difference. There should be something else as well. When we check the differences in molecular weight distribution, we see the difference. Usually, and based on literature, we know that the material with larger high molecular weight fraction tend to show higher ESCR. This suggests that the reason behind the ESCR loss in recyclates is not only PP contamination, but also something coming from differences in molecular weight distribution. This observation raises the next question. Where do these molecular weight distribution differences are coming from? One main important reason is that in the recycling stream, we mix different bottle grades with each other. There we have detergent bottles, we have milk bottles, juice bottles. Detergent bottles are typically designed to have high ESCR. They have the molecular weight distribution to have high ESCR. But for milk bottles, they're not going to be in contact with surfactants, so they don't use HTP grades that have this high molecular weight distribution, so they do not have high ESCR. But during recycling, we mix all of those bottles together. A hand-picking experiment by one of our colleagues also showed that in a typical recycling stream, only 40% of HDP bottles were detergent bottles. When we compare the effects quantitatively using design of experiments, we see that the negative effect coming from the difference in molecular weight distribution is larger than the PP contamination effect. This leads to an important conclusion. If we want to keep ESCR high, as it is in the detergent bottles, it's better to sort the bottles based on their type, not only by just removing the PP caps and PP contamination. In the next step, we try to find an additive that can improve this ESCR and can prevent ESCR loss in the recyclates. We have a lot of different additives in industry, olefin block copolymers, styrenic block copolymers, and most of them work as compatibilizers between HTP and PP. They can amend the negative effect coming from PP for the short-term mechanical properties, but most of them did not work for ESCR. We just found a styrenic block copolymer that significantly increased ESCR in both virgin grades and recyclates. And we tested in different grades, and we had 80 to 130% improvement in ESCR. We didn't find any mechanism in the literature that could explain this. And that was the kind of question that we wanted to follow in the next chapters. So we looked at different techniques to answer this question. Why ESCR is increasing by adding SEPS? Let's first look at the structure of this additive. This styrenic block copolymer is a SEEPS, styrene, ethylene, ethylene propylene, styrene block copolymer. These kind of block copolymers often have a soft rubbery mid-block and rigid polystyrene nanodomains arranged in a microphase separated structure. To understand how this affects the slow crack growth and the mechanism behind ESCR, we looked at strain hardening modulus. A strain hardening modulus is a very well-known indicator for slow crack growth and ESCR in the literature, and it works very well for virgin material. And it's measured, it also has an ISO standard, and it's measured from the slope of a strain hardening region in tensile test at elevated temperatures. When we check the strain hardening modulus results for HDP grades and for the blends with SEPS added, we see significant increase in strain hardening modulus. However, this improvement disappears as we increase the temperature and reach a temperature that, interestingly, is the glass transition temperature of polystyrene. To investigate this further, we performed FTIR tensile experiments. During that strain hardening region, the styrene peak shifts to lower wave numbers, indicating that polystyrene domains participate in load transfer. Together, these observations suggest that rigid polystyrene nanodomains contribute to improvement in ESCR indirectly. To understand how these domains interact with HDP matrix, we next investigated the morphology using different techniques. First, if we look at the SEM images, we see lamellar patterns in pure HDPE, and SEPS domains dispersed very well in the blend. When we look at the TEM images, we see those nanometric polystyrene nanodomains inside of those SEPS phase. And AFM confirming this SEM morphology shows also a gradual modulus transition at the interface. Together with additional evidence from tensile Sachs-Wax and DMA that I'm not showing here because of the time limits, we could conclude that there is an interface between SEPS and HDPE, and there the olefinic mid-block of SEPS can entangle with HDPE chains. Based on these observations, we propose the interface anchoring mechanism to explain why adding SEPS significantly improves ESCR. According to this mechanism, amorphous HDPE chains, including the tie chains, become anchored to SEPS phase that contain rigid polystyrene nanodomains through the entanglements in the interface. These anchors restrict the mobility of the tie chains and delay their disentanglement, because environmental stress cracking is strongly governed by these tie chains and its disentanglement. Delaying this process improves resistance to slow crack growth and environmental stress cracking. In summary, we started with 3 main questions and end with 3 main conclusions. First, loss of ESCR in recycled HDPE mainly originates from mixing different HDPE grades rather than from simply PP contamination. This means that sorting based on bottle type could preserve the tie chain concentration and improve ESCR in the recyclates. Second, among different additives that we tested, we found the styrenic block copolymer that showed improvement in both virgin and recyclate grades of HDPE, about up to 130%. We propose interface anchoring mechanism to explain why ESCR improves when we add this additive. This work has several impacts on several levels. Scientifically, it identifies the molecular origin of ESCR loss in recycled HDPE. It introduces a new mechanism that can describe additive-induced improvements in ESCR, linking morphology to crack resistance. It paves the way to design next-generation additives targeting this property. Technologically, it highlights 2 practical levers that can be implemented within existing recycling infrastructure without too much change: product-level bottle sorting and additive-induced ESCR. Environmentally, these findings enable high ESCR suitable for demanding applications, such as in detergent bottles, supporting EU recyclate targets, while reducing reliance on virgin material. Economically, improving recyclate quality increases its suitability for higher value packaging application and strengthens the market viability of mechanical recycling. In summary, this thesis transforms the challenge of limited ESCR in recycled HDPE from an empirical limitation into a fundamentally understood and technologically solvable problem. Thank you very much for being here and for your attention. I now give the floor back to the prorector.
Thank you very much for your presentation. Before we proceed with the opposition, let me briefly introduce this committee to the audience. On the other side, we have Professor Ragar, Professor Harings, and Professor Fiorio. They are the thesis supervisors. And on this side, on my far right, it's Professor Askes. Then we have Professor Van Rooij and Professor Bernards, who is the secretary of this degree committee. And online, we have two more members of the committee, which is Professor Pinter and Professor Govaert. In the next 45 minutes, questions will be asked by the members of the assessment committee, and the opposition will be opened by Professor Askes, who's Professor of Mechanics of Solids and Structures and Vice Dean of the Faculty of Science and Engineering of this university. Professor Askes, the floor is yours.
Thank you, Mr. Prorector. Dear candidates, thanks for having me today on your Defence Committee. I've read your work with interest. It's very well presented. It's very methodical, so I think it shows you're a clear thinker. But, of course, I have still a few questions left. Can I take you to page 12 first, where you describe the NCTL test, right? Which is, as the title says, a notched specimen. And I'll admit I am a computer modeler, so I don't know very much about lab work, but I take it getting a notch correct the way you want it is quite hard. So can you tell us how you control notch quality?
Dear highly esteemed opponent, thank you very much for your kind words and for the question. That's a very valid question about the notching. Controlling the quality really defines the quality of your results at the end. We really need to control the quality of notch. Instead, we end up with some scattered data at the end. To control this quality of notching, we checked some images with SEM to see the radius of the notch, but of course we cannot do this for all of the samples, because for that you need to destruct the sample itself. You cannot test it afterwards. But before each test, we checked each and every single sample by digital imaging, by a normal camera, and checked the ligament remaining by image J. So we were pretty strict on that. For these samples, we used a ligament of 0.595 to 0.605 millimeters, and that's because the wall thickness of detergent bottles is 0.75, and that's 20% of it. And anything outside of that range was disqualified, and success rate was something about 20 to 30%. So it takes a lot of effort and time, but it's worth it, because ESCR is a long test, and if you started with not correct samples, you end up with not good data. Also, I wanted to add something else, that with the notch quality, we checked the remaining ligament with SEM as well, and it was through the whole sample thickness uniformly at the thickness that we wanted.
So that's notch thickness mainly. Did I understand you correctly? You explained notch thickness?
The depth of the notch, yep, and the ligament thickness.
Okay, sorry, thank you. What about notch radius? To what extent were you able to control the notch radius? Because in a way, that's in my understanding, that's the critical parameter for fracture mechanics and fracture, therefore. Please.
Yeah, we of course, we cannot control that for all samples, because then you cannot do the test on that sample. But we did it for several blends and samples, and I put one of the images in the appendix as well. The radius that we had was around 5 micrometers. And also, we changed the blade every 10 to 20 samples according to standard to keep it sharp enough to have consistent sharpness of the notch. Excellent,
thank you. Can I now take you to page 75? You've got this figure 3.8 there, and the one that puzzled me was 3.8D. We have a bundle of curves, and there seems to be something going on with when you move from 5% weight to 10% weight, right? Are you nodding? That's good. So I picked something sensible. In the text, you mention matrix softening, and I don't disagree with you, but it doesn't explain to me that step change, that qualitative change from 5% to 10%. So can you take us a bit deeper into the material and explain what's happening there, if you can?
Yep.
And I'll say straight away, I don't know what the right answer is, so go for it.
Thank you. If you compare the creep test results for different additives that we used here, you see the clear difference for the ones at figure 3.8, and that's the one that you asked a question about. For this material, if we can look at the changes in the yield stress, maybe we can find something related to what's happening there.
So that's sub-figure A.
Yeah.
Yep.
There we see clear differences in yield stress when we move from 5% to 10%. So 5% and 2.5 are not that different from each other, but when we move to 10%, there's a clear difference. This, I think, might be one of the reasons, because when we are doing this ESCR test, we are applying a constant stress and we are keeping it, and the crack starts to grow slowly. At the end, it reaches some ligament remaining. Usually for the other samples, we don't see this much of ductile deformation at the end, but for this sample we see, because it's a kind of soft material that we added too much in this case, and it changes the yield stress. I think it changes the stiffness of material as well, and that's affecting the behavior at the tertiary stage of creep when we reach some critical minimum lengths of ligament remaining. I think this material starts to respond globally, not locally, and that's why we see this much of deformation.
Okay. And based on, I think I followed what you said. Based on what you just said, can you make a prediction what you think might happen if you go to 20% weight? Would it be another step change, or would it follow roughly the 10% line?
For the 10% sample, I don't think that sample failed at the end with this method of testing. So if we change it to the 20%, I think it even would start deforming earlier, but the elongation that it shows is out of the range of the testing equipment. That I cannot predict how much it can go. It's probably close to what we see from the tensile test. So from elongation at break, we see increase in when we have 10%. When we add it to 20%, I think we're gonna see too much elongation. But also depends on what kind of morphology we end up with.
That's fair enough. Thank you. Do we have time for another question, meneer de Prorector? Yep. Then on to page 141, please. So we're in your future work. So it's going to be a bit speculative. In the second paragraph, you start with future studies could therefore focus on establishing controlled loading conditions. Now, can you pretend to talk to your successor, whoever that may be, and can you expand a bit on what those controlled loading conditions might look like? Go for it.
So I think what we have done is looking at ESCR and slow crack growth with more of polymer physics and molecular reptation dynamics kind of view. And then on the other hand, in macroscopic scale, we have fracture mechanics. I think adding fracture mechanics here would add another dimension to this work, and then we can differentiate between the crack initiation and propagation. I'm not that much familiar with how to do these tests, so I know that we can do it with CRB tests, and changing the frequency and load would help to optimize the testing methods, but not so many details. I think if I want to do in the future, if anyone wants to do it with us in the future, I would do it as a kind of collaboration with experts, because in our group we don't have the equipment for that, and we don't have the expertise as well.
Thank you. Thank you.
Thank you very much. The opposition will now be continued by our online member, Professor Pinter, Professor in Material Science and Testing of Polymers at the Technical University of Leoben. Professor Pinter.
Okay, so hello everybody, and thank you, Mr. Prorector, for the work. At first, of course, I want to congratulate you to your very systematic and comprehensive work. I think saw a lot of new scientific results, but they also have, I think they are very good transferable also to real-world applications. So congratulations to my side. So dear candidate, of course, I have also some questions for you. I had another question as a starting question in my mind, but I want to go directly in a follow-up questions in the last from the last one, and you already mentioned fracture mechanics would make sense to go a little bit deeper maybe in this direction, and nevertheless I want to ask you, in your doctoral thesis on page 9 and 11, you describe the different methods that are available for having a deeper insight into EST, this failure behavior. And finally, in your work, then you use the strain hardening test and the notched constant tensile load test. Why have you chosen these two testing methodologies?
Dear highly esteemed opponent, thank you very much for your kind words and for the question. The reason why we did this method of ESCR that I have in my PhD thesis, maybe it needs a bit of introduction, because before I joined Kim's group, they had another project before that in Ghent University. So I did this project as a kind of follow-up to that with a big industrial partner. And we really did not have that much of choice which test to go with, because they wanted the data to be comparable with what they had and more relatable to the thickness that they have in the detergent bottles. That's why they go with this ASTM method. Strain hardening modulus, on the other side, was one of my favorites. Because it's a very well-known indicator. It has a standard for it, and there's extensive literature on that we can predict the way material would deform at the strain hardening region and kind of correlate that to what we see from ESCR tests. So that was a valuable addition to this work, and it didn't need too much sophisticated equipment. We had them fortunately in OMIBM, thanks to Jules, and so it was ready there, and I saw that an opportunity to add another dimension to ESCR measurements. And I think the similarity that we see from strain hardening modulus measurement and what happens when we have fibrils and slow crack growth is a good similarity, and it can help very much with a different kind of correlation. It works very well for correlating virgin material data, but with recyclates, we also had some differences.
And maybe in already knowing this, what is the big drawback of this measuring on looking at the strain hardening modulus now if you work with recycled materials? I think you mentioned it already in the answering the last question.
Yeah, thank you. With the strain hardening modulus, there are also in literature some papers that trying to add some prefactors to make it correlate with, to consider like short chain branching and those kind of differences. But the main problem with recyclates was that what we saw, at least in our samples with the strain hardening modulus, that when we do, for example, reprocessing and probably have some negative effects coming from the gels, that we don't see in the strain hardening modulus. So at least my results showed that the strain hardening modulus is not sensitive to this negative impact. Also, with the PP contamination as well, that was the case. So with environment stress cracking, we see negative effects coming from gels, coming from PP contamination, but that doesn't correlate with strain hardening modulus.
Thank you. Yes, the point, of course, with the strain hardening test is that it get maybe, of course, a lot of information about the mechanisms happening, but you do not get a lot of information, for example, of crack initiation. And there you have the problem with PP contaminations and maybe also with inorganic contaminations you can have in recycled materials, and maybe then you should use also other methods to have a look at it. And again, now my follow-up question. So the notched constant tensile test that already was discussed in a question before, with a focus on the notch. This is a very, what you are using, you're using a specimen that is quite thin, or so the specimen thickness is typically 4 millimeters, is this right?
If I understood correctly, the specimen is too thin.
The question is, how thick is the specimen?
Yeah, it's 0.75.
And the follow-up question is, looking at the stress and strain situation that you have in this specimen, typically, from my point of view, you have a typical stress-dominant situation. So that gives you, in the end, of course, a situation that gives you a more plastic-dominated failure. And I would say then, specifically, if you introduce a notch, you cannot keep the sharp notch because you have a lot of plasticity at the crack tip. With which other methods you could produce a more brittle failure?
That's a very valid question. I think that's because the thickness of the sample is dictated by the bottle thickness. Yeah. It's more relevant for the application itself. And of course, we were working with industrial partner on that. But to do it more, I would say, scientifically correct, I would go with thicker samples. I don't know much about the fracture mechanics, but what I remember is that when we have thin samples, we have the plane stress. And then when ligaments reach a very minimum size, the plastic zone makes it to respond globally. What we see from some of our samples with the block copolymers as well. I think for that, if we control the stress at a level that at the end we don't end up with samples that show plastic deformation after the failure, that's still good enough to satisfy that we are having a slow crack growth and it is relevant for application. I think that's what we do with the stress.
Very good, thank you. And maybe one more question, if it is possible, related to the mechanisms. Already in your introduction of your work, you're describing the different factors that affect the crack growth in polyethylene, in virgin polyethylene, and also in recycled polyethylene. You mentioned molecular weight, distribution, crystallinity, short chain branching, and so on. My specific question is now looking at time molecule entanglements. I think it's quite important looking also maybe deeply into crystallinity. Maybe can you comment on the effect of the lamellar thickness in the crystals? Can they be maybe positive affect the crack growth resistance?
Thank you for the question. If we increase the crystal thickness, then are we keeping the crystallinity same, or are we changing the crystallinity as well? Because they correlate.
Yeah, let me put it in that way. If we keep the crystallinity, then but changing the lamellar thickness within the crystals. Yeah. So same crystallinity, but changing the lamellar thickness of the individual lamellars. Could this be a possibility to optimize the crack growth resistance?
I don't know practically how it works to keep the crystallinity the same but change the lamellar thickness too much in polyethylene, because it's really hard to control material. Yeah. But if we can do that, then I would think of the Huang-Brown equation and how these change would affect that. Also depends, if we are keeping the crystallinity same, we are increasing the crystalline lamellar thickness, then it means that we are keeping the amorphous layer the same, or are we decreasing it? Because we are keeping crystallinity same, we are not decreasing the amorphous region thickness, right? And if it's the case, then for the minimum chain length to make a tie chain, we have the lamellar thickness plus 2 lamellar thickness plus amorphous thickness. And when we are increasing the lamellar thickness and keeping the amorphous thickness the same, so we're increasing the critical lengths that we need for a chain to make a tie chain, and then that wouldn't help ESCR, I would say.
Yeah, that wouldn't help. Yeah, so at this point, I think if it's possible, and I think there are ways maybe to change the lamellar thickness, then this could be an additional way maybe to optimize the crack growth resistance. Yes, thank you very much. Very happy with your answers.
Thank you very much, indeed. The opposition will now be continued online by Professor Govaert, who is professor in polymer mechanics at Eindhoven University of Technology. Professor Govaert.
Thank you. Thank you, Mr. Conrad. Geachte promovendus. First, I would like to congratulate you with your tremendous amount of work that you finished. I have a huge respect myself for predominantly experimental studies like yours, and especially in cases where they involve so many techniques. I'm really proud of that. Now, as an experimentalist myself, I, of course, have a few points to discuss with you. And I would like to start with the ESCR test, the results that you show in page 64, figure 3.2. Now, if I understood correctly, you use ASTM D6385 specimen. So you already mentioned this thin, and the width is something like 3 millimeter. You cut on one side, make a notch, and then you submerge them in a surfactant at 50 degrees Celsius, wait for 15 minutes, and then apply a load at 9 megapascal. Now, my first question is, the 9 megapascal, where did it come from?
Dear highly esteemed opponent, thank you very much for your kind words and for the question. If we look at the standard for doing this test, the stress that we have there is arbitrary. We can choose different stresses. It's not predefined, but it gives as an indication that we go for 1/3 of yield stress. And I think that's the stress that they chose at Ghent University before me, and we followed that here. I think that's exactly 1/3 of the yield stress of the bimodal polyethylene grade that we have in this project.
Well, if I can interrupt you, the yield stresses you measured in the range of 22 to 26 megapascal, and with the 9 megapascal, you are a little bit on the high side. Okay. Have not measured recycled materials, but grades we had a lot of experience on. And there you have a yield stress which is at room temperature on the low side of your materials, 22 megapascal. And at 50 degrees C, of course, this is a lot lower. It goes down to 14 megapascal. And if you look at time to failure purely plastically, so without a notch, and at 9 megapascal, at 50 degrees, that already will happen in the order of a day in polyethylene for a pipe grade of 22 megapascal yield stress at room temperature. Now, I cannot compare this value directly to your experimental results, but I guess that they are a little bit in the same order of magnitude, that you are in 1 to 10 days or something with your experiments?
Yeah, time to failure. Yeah, we had to put it a normalized way in the thesis, but it's a matter of days. Yeah.
Same order of magnitude. Now, if we look at the curves, then you see that they have some of the characteristics that you see in plasticity-controlled failure. You typically see primary, secondary, and tertiary creep, and especially the tertiary creep is in some of the curves quite markedly. You see it quite well. The fact that you see this and the order of magnitude in failure times makes me worry a little bit that the failure mode might not be crack growth, but plasticity controlled, similar like Professor Pinter mentioned just now. Now, to ensure that the fracture is brittle, you added some pictures in the appendix at figure S2, page 151. And when I look at that, then the first thing that comes to mind when I look at these pictures is that the fracture surfaces, they look symmetric. So it's like there is a horizontal line and it's kind of mirrored. So I don't recognize the pre-notch in these samples. Could you indicate where they are? How is it always on one side?
The notches at the top of the sample in these images that we are looking at. And the reason that we see that a bit symmetrical, that I think at the end of the test, when we have a very little ligament remaining, in some samples it's more plasticity controlled rather than a slow crack controlled. Mostly in the case of the olefin block copolymers added, or some of the additives in figure S4, for example. But when we look at the fracture surface, we don't see that much of deformation. So it's a kind of balance that we had to make our results correlated with the application in detergent bottles, because we couldn't have changed the thickness. As well as trying to keep it still up to some level at a slow crack growth controlled regime. And I think it works well.
Sorry, if I may interrupt you. What you might have done is reduce these 9 megapascal, because with every 0.5 megapascal, you shift plastic failure away by a decade. So if you would have done it by 8 megapascal, you would already have a lot more slack.
That is true. That is completely true. And of course, we are doing more ESCR tests nowadays. After my PhD, fortunately, I'm staying as a postdoc in the same group, and we have some ESCR projects going on. And that's the change that I already made to the samples that we are doing right now. We are doing samples with 5 MPa, 6 MPa, to avoid having these effects. But in the 2 first years of my PhD, I really couldn't change the stress there, because they wanted to compare all of their results with each other.
You need a bit more time.
Yes. And ESCR takes a long time. You know better than me.
Geachte voorzitter, heb ik nog tijd voor een heel klein vraagje?
Yes, of course, you can add one more question.
Okay, then I would like to go to chapter 4. In figure 4.3b, you kind of come with the first idea of how the seeps can give a positive effect on crack growth. And here I have a question, and the first question is, what is the long period of your system? So that is the thickness of your amorphous. How big is it?
That's a very good question.
Can you make the answer equally short?
Yes, yes, sure. We have the crystal thickness. I think you mean that we have those nanodomains of polystyrene, and those might be even larger than the amorphous region thickness. That's what you're asking, right?
Exactly.
Yeah, and that's
Exactly.
correct. And that's correct. And that's why we refined the mechanism in the next chapter. This was the first concept that we thought of, and at the time we didn't have most of the morphology results. And then with more evidence in hand, we tried to refine the concept.
Okay. Thank you for your answers.
Thank you.
Thank you for the discussion. The opposition will now be continued by the chair of the assessment committee, which is Professor Van Rooij, professor in plasma chemistry and chair of the Department of Circular Chemical Engineering at this university.
Thank you, Mr. Prorector. Geachte promovendus, also my congratulations with a sound, impressive thesis. And I always like when there are propositions. And in order to emphasize that appreciation, I would like to start a discussion with proposition number 5, and perhaps one of your paranymphe can read this proposition out loud.
Polymers behave like societies. Their properties arise from collective chain behavior, not from individual molecules.
Yes, I think also given the opening sentences of this session, by yourself referring to Iran, perhaps this is a sensitive proposition now. Perhaps you might also shed some new light on this proposition. I myself was, to start off, a bit confused because for me, polymers are molecules. And for you, the polymers are something else. And perhaps now, given the recent developments, perhaps you think that perhaps the individual molecules are determining society. Can you give maybe some thoughts on it?
Dear highly esteemed opponent, thank you very much for your kind words and for the question. I wrote this like a couple of months ago, so no, it was not, it was before what happened in my country, but it's related to what's going on these days there. Back to polymers. In polymers, we have, of course, we have other properties that may be because of one individual molecule, but mostly the mechanical properties, what we discussed in this thesis, for example, are defined by not one chain, but when when all of these chains collectively together respond to external stress.
Yeah, I think I was more interested in not the polymers, but the other ones. But I see you, that point I understand, thank you. Let's move on to the title of the thesis. I find it a very difficult one. Environmental stress cracking resistance. You have an abbreviation for it, ESCR. You quantify it, and I see that definitely because at some point you say, now my ESCR has become 100% better. Is when the ESCR becomes 100% better, the material twice as good, twice as valuable for the same price? How do I see this 100%?
Thank you very much for the question. When I say we have double ESCR, it makes that we improve that. But is it double better? Not necessarily.
No, I think we agree on that. So your test was double so good.
Sorry?
Your test became twice as good.
No, my test took twice longer.
Yes, so it became twice as bad, actually.
Yeah.
Very nice. Yeah, so I am a bit modest after the detailed discussion with the previous proponent. But nevertheless, I'm going to try, and stop me when I go wrong. That's the reverse situation compared to what we are normally dealing with in these commissions. But let's go to page 70, because there I started looking at these Yeah, I see big bars on the left, small bars on the left, big bars on the right. Then I get more interested in these curves. I like always curves. And in this left, in panel C, I see that curves break when they are low, and they break early when they are low. They break late when they are high. But then that's not the case in panel D, and it's not at all the case at page 74. So I'm wondering, you have normalized time. As a physicist, I find it an interesting value, but why don't you have normalized position? And should you have normalized position? Could you have normalized position?
About ESCR, it's time to failure, and the time to failure is the most important result of this test.
Yeah, for you.
Yes, but I think change in the position here mostly relates on how we perfectly zeroed the position at the beginning. So we cared about how this position changes mostly, but the most important results with the time to failure and how it changes.
Sorry, I see where you're going. Sorry, I want to cut you here because we have only a few minutes. Given the discussion that you had with the previous proponent, would also not be a very valuable behavior in these measurements, the steepnesses of these curves where they do not break yet? And would there be a correlation when it's weak, it moves fast, then there is plasticity perhaps? I'm talking about things that I have no idea about. Don't fool me.
Okay. If you mean the slope of the secondary step, the middle region? Or,
yes.
Oh, yeah. That's, if we have done the test correctly, is related to the slow crack growth. And if we have lower rate of crack growth, maybe that's related also to the ESCR value we get at the end. But from the results that I had, there was not a clear correlation, and I think it depends also on some other factors as well. Like, for example, if we have low yield stress, as mentioned by other members of committee as well, we might have some plasticity.
I'm going to stop you here because I have only 3 minutes and I see you are in safe zone. So I move on. May I take 2 more minutes? 2 more minutes, I hope 3. Let's immediately go. You had a fundamental insight, and you already promised that fundamental insight getting there in chapter 4, right? This anchoring. Yes, and you do measurements there, FTIR, I like that.
Yes.
And I'm an experimentalist, like my previous proponent, although the public here will doubt that. But I like the spectra. You have picked a peak, an arbitrary peak, and that moves to lower energy. But if I put all the figures together, I see that moving to lower energy. When the forces go up, do I interpret that correctly? What is here the value of moving peaks and different force and the fundamental understanding?
Yeah, thank you for the question. The reason that we are showing force here in figure 4.9 is that to show and correlate the timings between what's going on in the force time or stress strain curve versus what we have in FTIR spectra. And we wanted to show that whatever change that we see in the strain hardening region is what we follow with the peak shift in FTIR. That's why we are showing force. Why is it moving to the lower wave numbers? Based on the literature, it means when we go to lower wave numbers, it means that we are stretching the bond. If we want to go deeper, maybe it means that something is changing with the force constant. It means that we have probably a larger, as we look at the bond, something like a spring, we have a larger spring, it means...
Yeah, I see that point. But have you not been worried about in these spectra that you might also be looking at different regions as you are stretching, as the temperature is different, perhaps demixing, perhaps it's not a peak that you are looking at, but a convolution of peaks. Have you worried about these things?
If I understood correctly, you mean why did we choose
It's
this?
up to you. You have to be short, I'm afraid.
Yeah.
The reason
You can
that we-
continue during the drinks.
Oh,
You want?
Sure.
But
I'm
if you-
still
if you have a
very
short
satisfied with the answers.
Okay.
Let's.
Okay. The opposition will be continued by Professor Bernhardt, Professor in Sustainable Polymer Synthesis at the Maastricht Institute for Bio-Based Materials of this university.
Dear Pro-Rector, thank you very much. Dear candidate, it was a pleasure reading your thesis. I want to start with a general question. So you only studied the effect of unimodal and bimodal HDPE blending, but it's realistic that in waste stream you also have contaminations with ultra-high molecular weight PE or LDPE. How will the situation of the ESCR be in that case?
Dear highly esteemed opponent, thank you for kind words and for the question. In the recycling stream, and in this case from the handpicking experiment that I showed the results for, mostly we have HDPE bottles, and in that bottle stream, I don't think that we could have more of ultra-high molecular weight. I'm not sure. Mm-hmm. But what if we have? If we have ultra-high molecular weight, it also depends how well of blend we have there and how much of those chains we have in our molecular weight distribution. But I expect having more chains in case they can entangle and they can make good interaction with the matrix itself, can help having a stronger network, and it can work as a tie chain. It can improve ESCR.
In chapter 4, you use SEEPS as a compatibilizer, specifically one with an MW of 460,000 grams per mole. Would SEEPS with a molecular weight of 46,000 grams per mole still do the job?
If we divide it by 10, you mean?
Yeah.
So the question is, we have this interface anchoring mechanism. It works with SEPS. We have some molecular weight. What if we have lower molecular weight with that? That's a very good question. And I think we need a systematic study to answer correctly these questions, but I'm sharing with you what I really think about it is we need a minimum length of mid-block that can entangle with HDPE matrix. We are not sure that what minimum length that we need, but I think 46,000, 10 times lower, it would be challenging to make those entanglements. Speaking of, we have this mid-block that is not only HDPE blocks, but we also have a random copolymer there. So we really need longer chains in the mid-block, long enough to get this entanglement with HDPE matrix, to connect those domains of SEPS to HDPE chains so that this anchoring mechanism work. That's my hypothesis. Of course, I would like to do a systematic research later on that with using different block range of the styrenic block copolymer and the different percentage of styrene itself. All of these, if we can change systematically, would help to conclude much better. But you know, in industrial grades, you don't have that much of information, and it's really not easy to control it systematically.
Yeah. And in your studies, your block copolymers always had at the outer side polystyrene. Would a dye block with polystyrene block polyethylene/propylene also work?
If we have a dye block, then it depends what kind of morphology we expect from the styrenic block copolymer itself to form. I don't think with the dye block we can have the phase-separated morphology that we see with 3 blocks, and that's going to change the way the mechanism works. So I think if I want to conclude for this mechanism to work, we need a morphology that includes a mid-block that entangles with HDPE, and we need those styrene domains and a microphase separated structure within those SEPS. So you don't have either of them, it's not going to work.
Yeah, and related to those polystyrene domains, you of course are working on detergent bottles, so will your SEPS survive the presence of detergents? Because if this detergent is a good solvent for your polystyrene, are you still having the polystyrene domains?
That's a good question. I don't know if detergents can dissolve polystyrene. I'm not sure about it, but we know that the domains of SEPS and HDPE are small, like some micrometers. So it's going to be also game of diffusion and how fast it can diffuse and get to those SEPS. And then at the end, we don't have just polystyrene. We have polystyrene nanodomains connected to each other via a polyolefin mid-block. So it's going to make it challenging to solve.
Amir Khaki, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await our return in this room for the results of our deliberations. Thank you. Amir Khaki. The degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and by taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Ragar is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
All right, please.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I promise.
Then, by the authority vested in us by law, and in conformity with the decision of the committee here present, I hereby confer upon you, Amir Khaki, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I will now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dear Dr. Amir, there was a time, not so long ago, when my circular plastics group at Maastricht University was in fact just you. A very lonely PhD student with no office, no equipment, no colleagues, but loaded with enthusiasm and knowledge. What bravery to take that leap, to uproot yourself and Nasrin from your lives in Iran and to come here to what was for all intents and purposes still a blank page. But now, forever, the first name on that page will be yours. You have done excellent work, which is not only scientifically sound, but also immediately relevant to the packaging and recycling industry. I do not think your PhD will be fated to gather dust in a corner on a shelf. I think it will undoubtedly be read and shared actively. Amir, it is a very complicated time for you to be celebrating. War ravages your home country, causing the absence of your beloved family at this, your moment of glory and accomplishment. Us, the comfortable Europeans, cannot imagine the burden it must be to worry constantly for the well-being of your loved ones and the future of your native land. While on this larger scale of life and death, your graduation as doctor may seem trivial, I assure you it is not. It is the crowning of 4 years of hard work and a victory over the historical odds which have been internationally stacked against you solely based on where you were born. Do not let the acts of evil men take away from you the pride in your accomplishment. I have come to know you as a modest and good man, conscious of his effects on other people, and always hoping to leave the world a bit better than how you found it. What goes around comes around, and as a result, you have always been well liked by your colleagues. Look at the size of the audience here. You often help them and entertain them. I do not feel we should omit your very special brand of humor, which has caused as many rolled eyes as smiles. Thanks to you, almost everyone in the group now knows 1 or 2 very bad words in Farsi. And we will forever be inclined to ask, which Ali? Now, finally, I can return this favor and treat you to some excellent word jokes of my own, which I am sure you will enjoy as much as we have enjoyed yours. So, Dr. Amir. Which Dr. Amir? Because now there are 2 Dr. Amirs graduated under my care and even 2 Dr. Amirs in CCE. Oh yes, we can now make you regret your own worn-out joke. Here come the word jokes. Dr. Amir Khaki, throughout your PhD, you have been stressed and you have been strained. And while you may have deformed plastically on occasion, cracks may have initiated, but they have surely never propagated. By collaborating well with others, you created many time molecules, which protected you from slow crack growth and helped mitigate even the worst of impacts. Not in the least due to the anchoring mechanism of the support of your lovely wife, Nasrin, you've exhibited great resilience, and the required energy to break you, we were never able to exert it. You have crystallized our understanding of RHGPE, and for sure, I will be recycling your work in my slides for many years to come. End of stupid word jokes. I would say you leave behind more than just a scientific impact, but lucky for us, you're not leaving at all. I am curious to see how you will develop in this next stage of your career within the role of postdoc, which is no longer just about gathering knowledge, but also about sharing it onwards to younger researchers as well as industry. We already know you are a good researcher. Let's find out who you can be as a leader. My most heartfelt congratulations, Amir. I am very, very proud of you. And I am not the only one who is very proud of you. Your fellow promoter would also like to say a few words.
Thank you. Of course, I have to say something after this outstanding moment that we have here. So, dear Amir, 4 years ago, you took on the challenge of pursuing a PhD in a new country, in a young research group, and in a research field that still faces criticism from more traditional ones. But you were brave and you surpassed all the struggles. I have to remember here the nasty note that you got from on your poster during the first PPS that we attended together. With competence and professionalism, you faced all the problems and criticisms, responding to them in the best way possible, by conducting your research with excellence and delivering outstanding results. Working with you has always been easy and pleasant. You are the kind of researcher every supervisor hopes to work with. Curious, thoughtful, attentive to detail, and self-motivated. Basically, a natural-born researcher. It has been a pleasure and a privilege to supervise you. I'm very proud of you, grateful for your contributions, and excited to see where your next steps will lead. Congratulations, Dr. Amir Khaki.
Thank you very much. Dear Dr. Khaki, also on behalf of Maastricht University, I congratulate you with the doctorate degree that you have just acquired. My congratulations also go to your supervisors, to your wife, your family, and your friends. Now, before I close this meeting, I would like to thank all members of the degree committee. Your participation is much appreciated, no matter whether on-site or online. What's next? After closing this meeting, we will all go to the reception in the refectory elsewhere in this building, where you can all congratulate the new doctor. However, we also have a few online members, and I'd like to give them the word now so that they can briefly congratulate the candidate. And after that, we'll move to taking some pictures, where I also need the online members to stay around because you're also going to be in the picture. So let me first give the word to Professor Pinter.
Okay, thank you, Mr. Prorector, for the word. Dear Amir, it was a pleasure for me to read and evaluate your work. Personally, I started 30 years ago doing fracture mechanics in polyethylene, and I'm very happy that it is still of interest. So I want to congratulate you to your work, really, and to your results. They really open up new possibilities for using polymer recyclates in products and hopefully make our world a little bit more sustainable. Congratulations, Amir.
Thank you very much. Then Professor Govaert.
Dear Amir, congratulations on your PhD. I think your dedication and curiosity truly paid off. And I wish you continued success in your future academic and professional journey. And of course, very important, it's now also time to celebrate.
Thank you very much. Thank you all very much for attending this very special day in the life of Amir Khaki. I now close this academic meeting and we move on to pictures and reception. Thank you.